Welcome to Chapter 20 on Electrochemistry and the last chapter in Chemistry 1342, Electrochemistry. All right, so let's go ahead and get started. So electrochemistry, in this chapter we're going to examine how to balance oxidation-reduction reactions, the potential in volts generated by an electrochemical reaction, the total amount of current passed during an electrolysis reaction. We'll take a quick look at energy storage. We call those batteries. And your personal life with cell phones and laptops and cars is all run on batteries. So let's introduce you to the battery. This is a lead-acid battery, not a particularly efficient battery. You have them in all internal combustion engines. It drives the starter, gets your engine, your internal combustion engine going by turning it over. And so here we go. What we've got is we've got lead-4 oxide. I'm going to revisit this and just remind you of what you should have learned in Chem 1. And lead-4 is being reduced to lead-2. And since lead-4 oxide is being reduced, that makes it the oxidizing agent. Lead metal is being oxidized to the same compound, to lead-2 ions. It's being oxidized, and that makes lead the reducing agent in this reaction. So you've got the oxidizing agent. This is the oxidizing agent. You've got the reducing agent in this redox reaction. And that's the reaction that we have going. Reduction and oxidation, they happen together. The number of electrons lost will be the number of electrons gained. The lead-acid battery produces about 2 volts per cell. There are 6 cells in a lead-acid battery, assuming that you have some electrolyte in there, which is the sulfuric acid. That allows the electrons to be passed from one species to the other. And so the voltage is what we call a force that pushes electrons through the battery. And we want to know what chemical change is responsible for this force. Well, I've already mentioned it. I guess I was a little premature. And that is reduction, which always exists in tandem with oxidation, and we just call it redox for short. So a quick review. Oxidation is the loss of electrons. Something goes from a less positive to a more positive because it's giving up negative charge in the form of electrons. So this is copper. It has an oxidation state of 0. And if it goes from 0 to +2, it's giving up 2 electrons, and it is being oxidized. So copper is being oxidized in this reaction. So we'll use the little acronym OIL. Oxidation involves loss. Loss of what? Loss of electrons. So the oxidation state becomes more positive in oxidation. Something you were supposed to remember from Chem 1. Reduction is the gain of electrons. So here I've got a +2 charge, monoatomic ions. They get their charge. It's a +2. It's going to gain 2 electrons. So its oxidation state is being reduced to a 0 oxidation state. This is reduction, and we use the acronym RIG. Reduction is gaining, and gaining what? Gaining electrons. So the oxidation state becomes more negative. So oxidation is the loss of electrons. Reduction is the gain of electrons. Quick review. Oxidation states. Elements that are not in compounds always have the oxidation state of 0. So here is O2. And this is the elemental form of oxygen. It has an oxidation state of 0. I could say the same thing for iron metal. It has an oxidation state of 0. Or Cl2 gas. It has an oxidation state of 0, or nickel metal, it has an oxidation state of 0. That is, elements that are not in compounds. In their elemental form, their standard states, they have oxidation states of 0. Ions, the oxidation state is the charge of the atom or ion. So here we have copper 2+, it has an oxidation state of 2+. Here is oxygen with a -2 charge, we call that oxide. So this is oxide, and it has a -2 charge. Okay, its oxidation state is -2. Compounds, the oxidation states generally follow group trends. Start with the most electronegative atom. If I'm looking at a periodic table, the most electronegative atom on the periodic table is fluorine, and then you've got oxygen, nitrogen over here. So in general, elements that are in this part of the periodic table will be the most electronegative, and when I'm trying to figure out in a compound which atom is the most electronegative, so for instance we'll just use water. Oxygen is more electronegative than hydrogen. It gets its charge, which is -2. That means that in a compound which is electrically neutral, you got a +2, and of course we know that hydrogen is typically, not in every single case, but most of the time, you're going to see it as a +1 if it's in a compound. There are a class of compounds called hydrides where that changes, but we're not going to worry about those. All right, so, well, look at that. There's water. Oxidation state on oxygen, the most electronegative. This is the most electronegative. So we give it its charge, which is -2, and then we have to match up that with the 2 hydrogen atoms, so -2, -2, +2, and +1. Let's look at sodium hydroxide. So if I were going to do sodium hydroxide using this particular method, keeping in mind that sodium is an alkali metal, it gets its +1 charge. That's the only charge as an ion that we will ever see it in the natural world. Hydrogen is a +1. Well, actually, we could have started with oxygen because it is the most electronegative. It's a -2. That's a +1. It all has to add up to 0 for compounds. If I look at nitrate, so here's nitrate. NO3, it's got a -1 charge. It's not a compound. It's a polyatomic anion, so everything has to add up to a -1. So we've got oxygen. Oxygen is more electronegative than nitrogen. It gets its charge of -2. 3 times the -2 is -6. So you know, since -6 has to add up to some positive value to equal -1, it has to be +5. And so you've got a +5 over here on nitrogen. Here is perchlorate ion, ClO4. It's got a -1 charge. We're going to split these up, and again, the charges have to add up to -1. Now, oxygen is more electronegative than chlorine is, so it gets its charge, which is -2. 4 times the -2 is -8. We know that the charge or the oxidation state of chlorine has to add up to the -8 to equal -1, so that's going to be a +7. And so there we go. We've got an oxidation state for chlorine and perchlorate of +7, which it's not very happy about, to be honest about it. Chlorine would much rather be -1. This makes perchlorate ion a great oxidizing agent because it wants to reduce that big oxidation state of +7 on chlorine. So what is the oxidation number of manganese in permanganate, which is a good oxidizing agent? You can imagine it is going to be positive. So we're just going to use our little technique here. And if we've got a -1 charge on permanganate, oxygen is much more electronegative than the manganese ion. And so what we have here is 4 times the minus 2 is minus 8. Remember, it has to add up to minus 1, so we've got a plus 7 over here. And so plus 7A would be our solution. So what is the oxidation state of sulfur in S8? Well, this is a weird structure, but it's an element. And when you have structures like this, so this is sulfur, 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 sulfur. Let's see, 1, 2, 3, 4, 5, 6. And let's do a couple more. Sulfur and sulfur. That's pretty ugly, but 1, 2, 3, 4, 5, 6, 7, 8. So here I've got this ring structure for sulfur. There's no difference in electronegativity between one sulfur and the other, and since there's no electronegativity difference, sulfur S8 will have an oxidation state of 0. Remember, it's only going to be typically that elements in compounds have oxidation states that are more than 0 or less than 0, different from 0. So this is an element in an elemental form, and so it's sulfur's oxidation state is 0. And so we would list C as our answer here. Okay, identifying oxidation and reduction. What is being reduced, what's being oxidized in the following equations? Assign oxidation numbers to every atom. So this is zinc in its elemental form. Its oxidation state is 0. We'll use our little technique here. Chlorine is further up and to the right on the periodic table. It gets its charge. It's in group 7. It wants 1 electron. There's 2 of them. That's a minus 2. So over here we got a plus 2. And so that's going to be a plus 2. And over here, if we look at this compound, we go through the same process. 2 times the minus 1 is minus 2. This has to be a plus 2 because remember, everything has to add up to 0 for a compound. And so we've got a plus 2 oxidation state for zinc. Copper is an element in its elemental form. So zinc is going from 0 to plus 2. We call that oxidation. Now, whatever gets oxidized is the reducing agent. Okay, so zinc winds up being the reducing agent because it's going from a lower oxidation state to a higher oxidation state. Oil, as in oxidation is losing. Copper is going from a 2 plus to 0. It's being reduced. And any species that is reduced in a redox reaction, that makes this guy right here, copper 2 plus, or you could just say copper 2 chloride, that makes it the oxidizing agent because it's causing zinc to be oxidized. So that's how you analyze these. So zinc is 0, copper is plus 2, zinc's plus 2, copper is 0. Zinc is going to a plus 2, so it's being oxidized. It makes it the reducing agent. Copper is going from plus 2 to 0. That makes copper plus 2 the oxidizing agent. Okay. So quiz, oxidation and reduction. What's being oxidized in the following reaction? So you would just go through just like you just did, and we have a 0 oxidation state for sodium. We'd have to split water up, figure it out. Got a minus 2 here. There's only one of them, so that has to be a plus 2. Hydrogen is, if it's in a compound, in most of the equations you'll get, it'll be plus 1. Over here, if we're going to split these guys up, hydrogen's a plus 1, as I just said. Sodium is a plus 1. Plus 1. Oxygen is a minus 2. They all add up to 0. And then hydrogen in its elemental form, just as an element, it's got an oxidation state of 0. So what's being oxidized? Well, Sodium is going from 0 to +1. That's oxidation. That makes sodium the reducing agent. Okay? And water is being, the hydrogen actually in water, at least a couple of them, are being reduced to 0. There's your reduction. And that makes water, since it's being reduced, it makes it the oxidizing agent, or hydrogen in water is the oxidizing agent. So here you go. We've got these oxidation states, and since sodium is being oxidized, that makes it the reducing agent, and hydrogen in water is being reduced, that makes it the oxidizing agent. All right, the substance that is oxidized acts as the reducing agent. The oxidized substance causes reduction to occur. The substance that is reduced acts as the oxidizing agent, and the reduced substance causes oxidation to occur. So that the real shorthand in this is whatever gets oxidized is the reducing agent, whatever gets reduced is the oxidizing agent. So I would just put those two together. Whatever is oxidized is the reducing agent, and whatever is reduced is behaving as the oxidizing agent. What is the reducing agent in the following? Well, what are we going to look for? We're going to look for what gets oxidized. We already know that sodium is going from a 0 to a +1. It's getting oxidized, which makes it the reducing agent. Okay, so A would be our answer there. What is the oxidizing agent? Just getting a little bit repetitive here. We've got a +1 charge on on all of the hydrogens here. 2 of them get reduced, 2 of them don't, and it's going to 0. So this is the reduction, and that means water, or more specifically, the hydrogen ion that's the hydrogen that's in water is gaining an electron to become hydrogen, or actually 2 hydrogens in water are gaining an electron apiece, becoming H2. That is what's happening right there. Identify the element that is oxidized in the following reaction. So this is a little bit harder, but we're going to go ahead and we're going to work the problem. So we've split things up. Iodine is the most electronegative. It gets its charge, which is -1, and that's no surprise because sodium in compounds is always going to be a +1. All right, and then this is hypochlorous acid. Hydrogen's going to be a +1 over here. Oxygen's a -2, so we've got a -2 over here. And remember, this has to add up to 0, so you've got a chlorine, which is going to be a +1 oxidation state. Let's take a look at sodium iodate here. Leave a little bit of room. Iodine doesn't give me a whole lot of room. Oxygen gets its charge, -2. That's 3 times a -2 is a -6. Sodium gets its charge, which is +1, and so we need a positive charge that adds up to the +1 and the -6 to equal 0, because that's a compound, so that's going to be a +5. So iodine is sitting here with a +5. Over here, everybody's going to get their charge. Chlorine is in group 7, it's most electronegative, gets its charge of -1. Hydrogen, of course, is going to be a +1 in this particular compound. So let's take a look. This one's not so easy to see. Nothing's happening to sodium. It stays a +1. Iodine, on the other hand, is going from -1 to +5. That is a pretty big oxidation. Iodine is being oxidized a lot. in this reaction. It's going from -1, having an extra electron, to being short in this in its oxidation state of 5 electrons. So that's a 6 electron transfer. That's a big deal. Let's take a look at hydrogen. Hydrogen doesn't change. Chlorine, on the other hand, goes from +1 to a -1. That is a 3-time, that's a 2 electron transfer, and so that's a big reduction. We've got 6 electrons gained. We've got 6 electrons lost. And so identify the element that is oxidized in the following reaction, and that is going to be the iodine over here in sodium iodide.